Welcome to the deep dive. Today, we're tackling a whole stack of source material you've sent our way. It's all focused on, well, how computers actually interact with the real world.
Hmm.
We're going deep into output devices, the bits and pieces that turn all that digital data into things we can actually see or hear or, touch.
Exactly. Think of it as exploring the computer's voice.
Yeah.
And its hands, maybe. We'll look at the familiar stuff, sure, screens, printers, that kind of thing. But also the less obvious things, like the motors that make parts move or those systems for tracking packages wirelessly. Our mission really is to pull out the key stuff, the interesting bits from these sources, and help you get your head around how these devices work and, well, why they matter.
Right. So if you've ever looked at your computer and thought, okay, but how does it do anything outside the box? Then yeah, this deep dive is definitely for you. Let's get into it.
So at the most basic level, right, an output device is it's the component that takes the computer's processed data and makes it usable somehow outside the computer itself. That
Yeah.
could mean showing it to a human text on a screen, maybe an image, sound.
Uh-huh.
Or it could mean using that data to, like, control another machine.
Right. So it's not just about looking or listening. The output can actually do something, make
Yeah.
something happen.
Precisely. But
Yeah.
yet, the devices we bump into most often and the ones the sources start with are things like printers, screens, loudspeakers, multimedia projectors, the classics.
Okay, let's start with one. Most of us have a complicated relationship with printers, and the material breaks down a few different types.
Absolutely. Inkjets first. They're described as, well, the most common type out there. They range from really basic, cheap home models
Hmm.
all the way up to fancy professional ones for photos using loads of different ink colors for, better quality.
And this is where it gets interesting and maybe a bit annoying for us as users, right? The source really gets into the business side of inkjets. Often, the printer itself is sold super cheap, like suspiciously cheap.
Yeah, almost like a loss leader sometimes. Because the profit isn't really in the printer, it's in the ink cartridges. The source points out they have this huge markup. It even mentions that common problem where some printers just won't print black and white if, say, your yellow cartridge is empty.
Oh, I've definitely run into that. So frustrating. And the smearing ink, too, if you get the cheaper stuff.
That too, yeah. Cheaper ink often isn't very water resistant.
Okay. Let's shift gears then. Laser printers. Totally different beast, right?
Completely different. They use a dry powder. It's called toner. You can get them just for black printing that's monochrome or full color. And the sources really stress that businesses tend to favor lasers heavily.
Why is that then? What makes them the office workhorse?
Well, it really boils down to speed and reliability for, like, volume printing. They're way faster than most inkjets for documents, super reliable when you're printing loads, and the quality is excellent, especially for sharp text.
So for all those internal reports, company letters.
Exactly. The sources list things like company stationery, labels, maybe brochures or flyers printed in-house. Speed and reliability are just key when you're churning out hundreds, maybe thousands of pages.
Gotcha. Now, the source also talks about a type that feels almost ancient, but apparently it still has its place, dot matrix.
Ah, yes. Dot matrix printers, also called impact printers. They work kind of like an old typewriter, physically hitting an inked ribbon against the paper to make dots that form letters.
Wow. Why would anyone still use one of those?
Yes.
Seems so. Loud and slow.
They fill very specific niches, where the newer tech just doesn't cut it. The big one is multi-part forms, those carbon copy things. Because the pins physically strike the paper, they can press the image through several layers at once. Inkjets and lasers can't do that. Plus, they're tough. They can work in places that are damp or dirty, environments where a laser or inkjet would probably just give up.
Ah, okay. So durability in those special forms. Makes sense.
Right.
But downsides.
Oh, yeah, plenty. The source mentions the obvious. They're noisy as anything, print quality is pretty poor compared to modern printers, and surprisingly, they can still be quite expensive to buy initially. Definitely function over finesse.
It's interesting how old tech sticks around for those edge cases. Okay, let's jump from putting dots on paper to building whole solid things from materials. 3D printers.
Right. Now, this is where output gets really, really tangible. It just opens up so many possibilities. Like the source says, they can use all sorts of materials. Plastic filament is common, but also powdered resin, even ceramic or metal powder, paper sometimes. And the amazing thing is, they can build really complex shapes, things with, like, hollow insides or intricate structures that you just couldn't easily make any other way.
And the examples given for what they can actually make.
Yeah.
Working objects.
Mm.
It's pretty mind-blowing, especially in some fields.
Medicine is a huge one highlighted in the source. Making prosthetic limbs, orthotics. The cost reduction compared to traditional methods is apparently massive, and you get much greater accuracy. Think about it. Scan someone's limb, print a perfectly fitted custom prosthetic. It's huge for the patient and way cheaper.
The customization, yeah, and the cost saving. That's potentially life-changing stuff.
Totally. And it mentions surgery, too. Reconstructive surgery, general surgery. Surgeons can 3D print a model of the patient's specific anatomy to practice on before the actual operation, or even print custom parts needed during the surgery itself.
Wow. Practicing on an exact model first. That must improve things significantly. Safety, planning. And the source throws out that really big question, doesn't it? Could we ever print a whole new human organ? That's future stuff, but it makes you think.
It really does. It shows how fast this is moving. But it's not just medicine. Manufacturing, art.
I like the car parts example.
Yeah, that's a great one. Making parts for, say, classic cars where the originals are long gone, you can just scan an existing part, maybe even a broken one, use it as a blueprint and print a replacement. Saves a fortune compared to traditional tooling. And that same idea, blueprinting, rapid prototyping, slashes costs in design, fashion, art. You can iterate so much faster.
So yeah, custom stuff, repairs, saving money, enabling new designs. The potential seems enormous. The source definitely paints a picture of this becoming more common.
It does. It lists possibilities in manufacturing, home use, medicine again, marketing, architecture, education, even archaeology. It feels like we're just seeing the beginning.
Right. But like with any powerful tech, there's always a flip side, right?
Yeah.
A potential danger. The source brings up a major concern with 3D printing.
It does. It flags that incident from 2013 where the digital file, the blueprint for printing a working handgun, was created and shared online. And that immediately raises some really serious questions. You know, who could print one if the design is just out there?
And the material itself.
Yeah.
If it's mostly plastic.
Exactly. What does that mean for security? A plastic gun might, potentially, get through traditional metal detectors. The source definitely flags this impact on security at airports, buildings. The sobering reminder, really, that as output tech gets more powerful and easier to access, it throws up new challenges. Safety, regulation. We need to think about this stuff.
Yeah, it really drives home that the output isn't always neutral. It can have real, sometimes difficult consequences. Okay, let's shift focus a bit. Moving away from physical objects to other ways computers output information or control things.
Okay. Well, one interesting system the source covers is RFID, radio frequency identification. These are actually input and output devices because they send and receive data wirelessly. You basically have two parts. The tag, that's the transponder, and the reader, the receiver.
And how do they talk to each other?
Well, the reader sends out radio energy. The tag, which could be in your bank card, your phone, a sticker on a product, even under an animal's skin, has a tiny antenna. This antenna picks up the reader's radio waves, gets energized by them, and uses that energy to send its own stored data back to the reader.
Ah, so the reader actually powers the tag wirelessly, so the tag can respond.
For passive tags, yes, exactly. That's a key difference the source points out. Let's talk uses first, though.
Right, the source listed quite a few.
Yeah, security and ID are big ones, tracking people, animals, valuable items. They're massive in shipping and supply chains. You can track stuff automatically, in real time, without needing to physically scan a barcode. Imagine tracking a whole pallet of goods as it moves through a warehouse, just wirelessly. It's a huge leap from manual scanning.
That automation. Yeah, you can see why businesses would go for that. Cuts down on manual work in warehouses, logistics.
Absolutely huge efficiency gains. They're also used in banking, obviously contactless payments on cards, phones, and they're seen as potentially replacing barcodes in many places because you don't need that line of sight scanning.
Okay, you mentioned passive tags before. What's the difference between passive and active?
Right. So passive tags, like in most bank cards or shop security tags, have no battery, none at all. They completely rely on the energy from the reader's radio signal to wake up and talk back. That's why you have to hold your card, right up close to the payment terminal. It needs to be in that strong radio field.
Makes sense. And active tags.
Active tags do have their own little battery. They act like tiny beacons, actively broadcasting their signal. The source says they can transmit much further, up to 300 meters, so they're better for tracking bigger things you don't handle individually or things you need to read from further away, like shipping containers, cars going through tolls, maybe tracking assets in a massive warehouse.
That range makes a big difference for those kinds of applications. Okay, moving from identifying things to physically moving things, actuators.
Actuators, yeah. Think of them as the computer's muscles. The source describes them basically as motors that are often used with sensors. They get a signal from the computer, and they turn that signal into physical movement, controlling some kind of mechanism.
Okay, like what? What are some real-world examples?
The source lists things like opening or closing a valve, maybe a door, starting a pump, turning a wheel or a fan, or even moving, say, the control surfaces on an airplane wing like an aileron. Pretty much anywhere a computer needs to physically do something based on data, you'll likely find an actuator making it happen.
Right, the link between the digital command and the physical action.
Got it.
And finally, in this sort of category, audio output. Speakers, headphones, how does the computer's digital stuff become sound we hear?
Okay, so the process described starts with the digital data, right? The ones and zeros from the computer. This gets sent to a really crucial bit of kit called a DAC, digital to analog converter. Its whole job is to change that choppy digital signal into a smooth, continuous analog electrical wave.
Because speakers need that smooth wave, not the digital numbers.
Exactly. The DAC guide does that translation. Then, that analog signal usually goes through an amplifier to boost its power. And then finally off to the speaker or headphones. The electricity makes a little cone or diaphragm vibrate, and those vibrations make the sound waves we perceive.
That DAC step digital to analog seems absolutely critical then.
Okay, let's spend a bit of time on arguably the most common output device we all use constantly, the screen.
For sure. LCD monitors liquid crystal display, they're everywhere. The source explains they work using tiny groups of red, green, and blue diodes for each pixel. But the key thing is, the liquid crystals themselves don't actually make light. They act more like tiny little shutters or valves controlling how much light passes through.
So they need a light source behind them. Precisely. A backlight. Originally, this was often done with CCFL's cold cathode fluorescent lamps, kind of like miniature fluorescent tubes. But pretty much all modern LCDs use LEDs for the backlight instead.
Right, LED backlighting. And the source goes into quite a few advantages of using LED's light-emitting diodes over those older CCFLs.
Yeah, the benefits listed are pretty significant. LEDs hit full brightness almost instantly, no warm-up time like fluorescents. They generally give you a sharper picture, more vivid, realistic colors. The light's brighter, too, which helps with definition.
And they physically changed how screens look, didn't they?
Massively. LEDs are tiny, so using them as a backlight meant screens could get much, much thinner than they ever were with CCFL tubes. They also last way longer, making screens more reliable, and they use less power and produce less heat. That's huge for running costs, battery life in laptops, that kind of thing.
Thinner, brighter, longer lasting, more efficient. Yeah, you could see why LED backlighting took over, but now there's something even newer starting to dominate, especially in phones. OLED.
OLED, organic LE, that's another big step. The source describes them as even thinner and lighter than LED backlit LCDs. And one really cool thing is they can potentially be flexible because they often use plastic instead of glass.
Flexible screens. That still feels like sci-fi. What are the main advantages of OLED that the source highlights?
Well, the biggest one is that each OLED pixel makes its own light. There's no need for a separate backlight layer at all. Getting rid of the backlight makes them simpler, thinner, and crucially, it means they use way less power, which is fantastic for things that run on batteries, phones, tablets, smartwatches. Makes the battery last longer.
Less power and less heat, too, I guess.
Exactly. Less heat generated, which is good for reliability and safety. And they tend to have a wider viewing angle than LCDs. You can look at them from the side more easily. Plus, the source mentions this is enhanced by curving the screens, which you see on some high-end TVs and monitors for a more, immersive feel.
Lower power, better picture, potential for flexibility. Yeah, it's clear why OLED is their premium choice now, especially for mobile stuff. Okay, one last visual output device. Projectors.
Multimedia light projectors, yeah. The source describes them as compact, high-res, full-color devices. They can project pretty much anything: text, images, video, even handle audio. They usually take input from a computer, maybe a Blu-ray player, or even a USB stick.
And their basic job is?
Take that video signal, whatever the source, process it, turn it into an image, and then use light and lenses to beam that image onto a screen or a wall. Common uses are things like PowerPoint presentations, watching movies or TV really big, playing video games.
Okay, so we've gone from ink on paper, building solid objects, tracking tags wirelessly, making motors turn, creating sound, and displaying images on these amazing screens or throwing them onto walls. That pretty much covers the gamut of how computers output stuff, right?
It really does.
Oh.
And if you pull it all together, you see how each technology solves a different problem, uses that computer data in a specific way. A laser printer for that sharp business report, a dot matrix for that niche multi-part form, a 3D printer making a custom medical device, RFID tracking packages, an actuator opening a valve, the OLED screen on your phone, a projector in a meeting. They all have their place.
So for you listening, what's the big picture here? Why should you care about all these different output devices?
Well, I think understanding this stuff gives you a much better feel for how the digital world actually connects to and influences the physical world around us. It helps make sense of why certain tech is used, where it is why a hospital might invest in 3D printing, or a logistics company uses RFID, or why your phone screen looks so good and the battery lasts longer now. It can help you choose the right tech for what you need to do. And maybe importantly, like we saw with the 3D printed gun example, it helps you appreciate both the incredible power and the potential downsides or societal questions these technologies bring up as they get more advanced and more embedded in our lives. It's really about seeing computation made real.
Yeah, it definitely shows the computer isn't just stuck inside its box. It reaches out through all these interfaces, from something as simple as printing a page to something as complex as making a custom implant or tracking goods globally. Output devices are kind of the unsung heroes making the digital physical.
Absolutely. And as these technologies keep getting better, I mean, think about where 3D printing could go, or truly foldable, rollable screens. Who knows what's next? Which kind of leaves us with a final thought for you to chew on. As these output capabilities get even more sophisticated and woven into everything we do, what totally new ethical challenges or societal shifts might pop up, things we maybe haven't even considered yet?